Welcome to qnawire.
Okay, in this problem we have an electron beam with electron energies of 40 eV. It passes through a single slit with a width of 5 times 10 to the negative 6 meters, so micrometers. And it travels beyond the slit 2.5 meters onto a screen and creates an interference pattern. And because these electrons have wave-like properties with a de Broglie wavelength, they're going to make this interference pattern in the same way that light would. So we're first asked to find what this wavelength is for these electrons. We're then asked what's the time it takes for the electrons to travel to the screen. And we are finally asked for the uncertainty in the y-directed momentum of these electrons. So to start off, we'll need to know the definition of a de Broglie wavelength, some basic definitions for energy and momentum, the single slit interference equation, and note for the first minimum, the n constant is 1. So actually I should perhaps explicitly include that. For our case, n is going to equal 1. And of course, we need Heisenberg's uncertainty principle to relate a uncertainty in position and uncertainty in momentum to the Planck constant. For constants, we use the electron mass and reduce Planck's constant. So let's get started. So to start, let's get this wavelength of a electron. So it's h over the momentum. We can express a momentum. Let's go off to the side. So if momentum is mv and k, the kinetic energy, is 1/2 mv squared, we can combine these two expressions to say that k is equal to momentum squared over 2m. So we know the kinetic energy of these electrons, it's 440 eV. Thus we can throw this in for momentum, eliminate it from the equation, and express the wavelength in terms of energy only. It ended up being root 2 times m times k. And plugging in the Planck constant, this is not h bar, the reduced Planck constant. This is just the regular Planck's constant, which is reduced Planck's constant times 2 pi. Plug everything in, we get a wavelength of 6.136 nanometers. And that's the first part. Now that we know lambda, although I don't think we actually will need it, to find the time it takes, the time of flight to go from the first slit across to the screen, we can simply take a distance divided by a velocity. And we know the velocity because we know the kinetic energy. So we can express this as delta x multiplied by root m over 2k. Putting our numbers in, we have 6.66 times 10 to the negative 7 seconds. So these electrons are moving relatively fast. They'll arrive at the screen very fast. Now we actually need to make note of this interference pattern. So recall from single slit interference, when we were studying light, a sine theta is equal to n lambda. If we're only interested in the first minimum, going off to the side from the central maximum, n is equal to 1. Thus, we can find theta which is simply arc sine of lambda over a. We know lambda, we know a, we can find theta. It comes out to about less than a degree. So why do we need this? We need this because once we know this angle, we can then get the ratio between the y momentum and the x momentum. Drawing a little picture. Here's the screen. Here's a slit. We now have an angle. And we can relate this to the ratio of momenta, assuming that a particle goes straight from the slit to this minimum, or in this case, it will never go to the minimum. So we can use the uncertainty principle. Delta y, delta py, greater than or equal to h bar. Thus, the uncertainty momentum will be h bar over lambda, or rather h bar over delta y. And we can figure all this out. This comes out to be 8.64 times 10 to the negative 33 kilogram meters per second. And that's all we're asked to solve. So the hardest part here is relating the geometry of the situation to get the ratio of, to understand what py will be. That's the tricky part. So once we have our delta y, we can find py. Okay, so those are the main results. Found lambda, found the delta t, and we found uncertainty and momentum in y direction. And that's it.